Good evening, friends, and I'm back with fourth session of Electrodynamics in the Aspire series. I hope you liked the previous sessions, and let's have a look at this session today. The topics that we are going to cover in today's session would be electromagnetic induction and alternating currents. All right, so I have brought some questions here for you guys. I hope you will like these questions. Let's get started already. And for our new viewers, for those who are viewing me for the first time, let me just give a brief introduction of myself. My name is Vikas Sir. I have done BTech in Aerospace Engineering in the year 2008 from IIT Kharagpur, and since then I have been into IIT JEE teaching, and I have taught in coaching institutes such as Resonance, Bansal Classes, Career Point and FitG, and recently I have joined Vedantu. So that goes about me. Let's get started already as we are very short on time. Okay guys, so before we start, I would like to tell you about our doubt solving app. So do download this app, use this app. This is for your benefit. So guys, make sure that you're using it. All right, and if you like our videos, I'm sure you do like our videos. So guys, please click on the like button, share our videos with your friends and family, and do subscribe to our channel. That's a request from my side. All right, now let's get to the academic part of this presentation. So guys, we have a question here. Let's read the question and let's try to attack this question. Okay, the question says a coaxial cable consists of two thin coaxial cylinders, okay, electrically connected at one end. I'll get out of the frame so that you can read the question. Okay, so coaxial, an inner cylinder of radius 10 millimeter and a steady current 1.7 ampere, which is screened by at outer cylindrical conducting sheath of radius 20 millimeter. All right, which provides a return path. Assume that there is no dielectric medium present. Total magnetic energy present between the space of the conductors. Okay guys, so I believe you have read this question. Let me try to explain this question to you, then we will solve it on the next page. Okay, so see guys, since a figure is not given in this question, so it may just make it a little bit difficult to understand the question. Okay, generally figure helps us in understanding. So this question is lacking the figure, although the information, adequate information has been given to us so that there is no ambiguity regarding the situation. Let me just help you with the situation. So we have two coaxial cables, like you can imagine a hollow cylinder like this. Okay, and this hollow cylinder is surrounded by another hollow cylinder. Okay, so let me draw it like this. All right guys, so this is the situation. Okay, there are two hollow cylinders and they are coaxial. It is given that they are coaxial cylinders, so their axes are coinciding, as you can see in this figure. And we can also see that the radius of one is 10 millimeter and the radius of the second one is 20 millimeter. That is, this is 2 times the radius of the inner cylinder. Okay, so what I'm going to do, I'm going to denote R1 by R. Okay, and this would become 10 millimeter. Okay, and I'm going to denote R2 by 2R. Okay, and this is going to become 20 millimeter. Okay, so like R is 10 millimeter, so I will be writing the expression in terms of R, and in the final step we will substitute 10 millimeter in place of R. All right, so this is the case. Now regarding current, so the question says that it carries a steady current of 1.7 ampere. Okay, and like one of the cylinder carries current in one direction. So as far as the current is concerned, let me tell you what is going on. So like if this inner cylinder is carrying current in the upward direction, like current is flowing on the surface of this cylinder. Okay, you can imagine a hollow cylinder here. ठीक है, जैसे ऐसे एक hollow cylinder है, इसकी पूरी surface पे नीचे से ऊपर की तरफ current run कर रहा है. ठीक है, so situation is something like this. ठीक है, you can extend these arrows up to like infinity. Then यही करंट फिर बाहर वाले वायर से और this current, the same current is coming down from the outer cylinder. Okay, so is this situation clear to you guys? And let's say the length of the cylinder that we have to consider is 1000 millimeters, so 1000 meter actually. Yeah, so 1000 meters, so that's quite long, that's very long. Okay, 1000 meters is basically 1 kilometer. So we can say that we are dealing with an infinite cylinder. Can we say that? We can definitely say that, because the length is very large as compared to the radii. Okay, so we can say that we are dealing with an infinite cylinder, hollow cylinder carrying current. Okay, in fact we have two cylinders. Okay, now let's say if we are viewing this situation from the axis. Okay, for example, if this is the eye of the observer. Okay, eye, aankh. Okay, if this is the eye of the observer, what kind of figure is he going to look? Okay, so let me draw that figure on the next page. Okay, So I hope the question is clear to you. We have been asked the magnetic energy stored in the space between the cylinders, and I hope you can understand why magnetic energy will be stored there, because there will be some magnetic field. Let me help you with that magnetic field now. Okay, so I was talking about the view of an observer who is looking from top. So for a person who is looking from top, okay, the inner cylinder will appear like this. Obviously I'm drawing a enlarged figure now, okay, and the outer cylinder is going to appear like this. I hope they are looking concentric. Yes, probably. So this becomes the axis of both the cylinders, which will appear as a dot. I hope you are able to appreciate this one. Okay, and current, the inner cylinder is carrying current towards the observer. Okay, so we are going to witness dots here, and guys, these dots do not indicate the magnetic field line. I'm using these dots to indicate the current coming out of the plane of the board. Okay, so I'm using these dots to indicate current. This current is coming out like this, then it is moving to the outer cylinder, and this joint between the inner cylinder and the outer cylinder is at infinity. So it's coming out like this, it's going to the outer cylinder, and then it's going back again. Okay, so in this cylinder, can we say that the current will appear in the form of crosses? Do you agree with this one, guys? Can we say so? Okay, we have still not started solving the question. Let me tell you that I have still not started solving the question. I am still explaining the condition of the question. Okay, what is given in the question. All right, so what kind of magnetic field are we going to witness? So this cylinder, this hollow cylinder which is carrying current in the outward direction, is going to produce an anti-clockwise field, and that will be like this. Okay, and this cylinder will produce magnetic field in this region also, in the region between the cylinders, and it will produce a magnetic field outside also. But having said that, this outer cylinder, okay, this outer cylinder will produce a magnetic field in the clockwise direction. Okay, and if we are considering a point which is outside the cylinders, okay, so what will happen? The inner cylinder, okay, the inner cylinder is creating an anti-clockwise B here. Okay, let me write it as B inner. The outer cylinder is creating a clockwise B, so that would be negative in downward direction, and this is because of the outward cylinder. And since they are carrying same current, and magnetic field at outer region of a cylinder is dependent on the distance from the axis. So this distance is same for both the cylinders. Both the cylinders are carrying the same current. So what do you think, guys? Is this going to get cancelled? Okay, so that is indeed the case. So what can we say right now regarding this situation? In this situation, whatever magnetic field is present, that is present between the two cylinders only. No magnetic field is present outside the two cylinders, or in the region which is outside to the outer cylinder. So in this region we do not have any magnetic field, and hence we do not have any magnetic energy also. In this region we have magnetic field, and hence we have magnetic energy also. And moreover, in this region the magnetic field is definitely non-uniform. Okay, the magnitude will vary, the direction is also varying. So this is the situation as far as the question goes. Now let's come to the question, and let's try to solve this question. The question asks for the magnetic energy that is stored between the cylinders. So in this region, whatever magnetic energy is stored, that is what we want to calculate. So I hope the question is clear to you. Okay, I hope the question is clear to you, and now let's see how we are going to solve this question. So guys, any ideas, any hints that you are getting? So I'm going to use the expression for magnetic energy density. Okay, and I hope you are aware of this expression. The energy for magnetic energy, the expression for magnetic energy density would be B square by 2 mu naught. Okay, so this would be the expression. So this is what I'm going to use, and how I'm going to put it to use. Okay, I'm going to choose an element. I'm going to choose an element of, let's say, radius x and thickness dx. Okay, you imagine a cylinder here of length L dx thickness. ठीक है, dx thickness का एक cylindrical region imagine करना है. ठीक है, मैं इसको पूरा नहीं बना रहा हूँ क्योंकि पूरा सर्कल मैं बना नहीं पाऊंगा, वो गड़बड़ हो ही जाएगी. ठीक है, I will not be able to draw a complete nice circle. Therefore I'm not drawing it. Okay, I'm not sure whether this blue color is visible to you or not. I got a feedback in my last video that please don't use the blue color. So let me just redraw it with red color. Okay, so we have chosen an element of radius x and width dx. Okay, and this is a cylindrical element. So let me just draw the shape of this element to help you understand what is going on. Okay, so let me draw the shape separately. So this kind of element is what we are imagining. I hope this figure clarifies something. Okay, and this length is L, which is actually 1 kilometer. Okay, so guys, what will you say? What are you going to say regarding magnetic field at a distance x from the center? Okay, let me erase this one now. Okay, let me erase this one. We'll be using this figure. So let me erase this one. I need some space here. So let me erase this one. Okay, so what we are going to say regarding the magnetic field? The magnetic field will be mu naught I by 2 pi x. What do you think, guys? This region is like outside the inner cylinder. So the inner cylinder will act as a wire, as an infinite wire, and this is the amount of magnetic field that it is going to produce. And the contribution of the outer cylinder will be 0 because the region in which we have considered the element lies inside the outer cylinder. So the outer cylinder will not contribute anything. Okay. Now, as far as the magnetic energy density is concerned, we can calculate the density from this. Okay. So let me write du. Now, what is du? Du is the energy present within this volume. Okay. This elemental volume. So I'm first writing this volume. Okay. Pay attention to how I'm writing. I'll first write the curved surface area of this element. So guys, will that be 2 pi x into L? Just see this if you are able to get this or not. The curved surface area of this element will be 2 pi x into L. Is this clear to you guys? I multiply this curved surface area with the thickness. Okay. For example, if you imagine that we cut this cylinder with a scissor, if we are able to do so, okay, and we open it, then we are going to get a rectangle of area 2 pi x dx, and the thickness of that rectangle would be dx. So the volume of this cuboid, okay, this very thin cuboid that we are going to get would be 2 pi xl into dx. Okay, so this becomes the volume. Now we multiply this volume with magnetic energy density. So that would be mu naught I by 2 pi x, okay, square into 1 by 2 mu naught. So this is the energy present within this volume. Ab kya baki hai? What is left, guys? So to get the total amount of energy is present, we are going to integrate this expression, and the limits of integration will be from what? R1 to R2. Okay. So once you finish this integral, you are going to get the answer. I'm skipping the calculation part of it because I'm very sure that if you are watching this video, you have most probably qualified for advanced, and if you have qualified for advanced, I think you yourself wouldn't want me to do the calculation. Okay, that is something that you can definitely do. I'm very sure of it. So I'm not going into the calculation part of it. You can just see the procedure here and you can follow this procedure. Whatever you are going to get from this calculation, that will be the correct answer. All right. So once you do the calculation, we expect you to get 0.2 millijoule. Okay, I've done this question. I've solved this question once. So the given answers are correct. Okay, unless the typist had made some errors. Okay, so you can just finish the calculation and you can see for yourself. I hope I'm able to explain you the procedure and the approach behind this question, so you'll get the answer. All right. Okay, now let's have a look at the next question, which is related to this question only. So we are very aware of the situation. We are good with the situation. We are aware of it. So till this part, everything is same. Now the question asks about the self-inductance of this arrangement. Okay, guys. So since we have calculated the energy present in this region, okay, we can straight away give the self-inductance, and the self-inductance can be given by this expression half Li square. Guys, is this the energy stored in the inductor? Okay, so the answer that we have already calculated in the previous part, you use that answer to get the value of L. The value of L will be 2E by I square. You do this calculation, you're going to get the answer. One of the options you are going to get, and that will be the correct option. Okay, now having said that, was there any other method to get this answer? Okay, so let's see that. We have got the answer. And in the examination, this is preferred, like this would be the most preferred method because the previous question asks us to calculate the energy. Once we are done with calculating the energy, this is the most obvious thing that we should do. Okay, but let me tell you, there is something else that what we could have done. Okay, so let me tell you that method. Okay, I drew the field like this was the cylinder and this was the another cylinder, and the region between them, okay, the region between them was having magnetic energy. Okay, and the field lines were like this. Okay, the field lines were like this. So guys, you'll have to imagine something now. Okay, imagine a rectangular surface in this region kept like this. ऐसे सीधी जा रही है, दो साइड्स रेक्टेंगल की, एक साइड ऐसे है, और मतलब एक हॉरिजॉन्टल प्लेन में एक रेक्टेंगल इमेजिन करो. ठीक है, लेट मी टेक एन ऑब्जेक्ट टू हेल्प यू. एक विजिटिंग कार्ड पड़ा हुआ दिख रहा है मुझे यहाँ पर. तो ऐसा एक सरफेस इमेजिन करने को बोल रहा हूँ मैं. ठीक है, जिसकी जो चार एजेस है, द फोर एजेस आर लाइक दिस. ठीक है, 1 2, सो दीज एजेस. ठीक है, शो करता हूँ थोड़ा सा. ये जो एजेस हैं, दीज एजेस आर 1 किलोमीटर लॉन्ग, दैट इज द लेंथ ऑफ द सिलेंडर. ठीक है, एंड दीज एजेस आर R2 minus R1. दिस वन इज R2 minus R1. ठीक है, तो लेट मी शो यू द थिंग अगेन. You have to imagine this length is 1 kilometer, this edge is 1 kilometer, and this edge is R2 minus R1. So we make this rectangle horizontal and we imagine that this rectangle is present here. ठीक है, ऐसे. तो guys, I hope you are able to imagine the rectangular surface that I'm trying to explain. And if that is clear, just tell me whether some magnetic field lines are penetrating through this rectangular surface. Do you agree with this, that there are some magnetic field lines that are penetrating through this magnetic surface? And if that's the case, then we can talk about the flux through this rectangular surface. So let me do that. I want to calculate the flux through that rectangular surface. So how we are going to do that? We are again going to assume an elemental strip. Now ये जो चीज़ है, मैं ये strip मान रहा हूँ. I'll tell you what I'm doing. So the rectangular surface that I am referring to, okay, the rectangular surface that I am referring to is like this. ठीक है, ये लेंथ L है और ये लेंथ है R2 minus R1. ठीक है, सही है. Now what is dx? X distance पे dx. So this is basically dx. See whether you are able to get this or not. This is a strip of length L and width dx. This rectangle is present here. ठीक है, ऑब्वियसली ये वाला व्यू नहीं है, हमको यहाँ पर रेक्टेंगल रखा होगा तो केवल उसकी ये फ्रंट एज नजर आएगी. फॉर एग्जांपल इस कार्ड को अगर मैं होल्ड करूँ तो देखो तुम्हें क्या नजर आ रहा है. तुम्हें सिर्फ ये थिकनेस नजर आ रही है. ठीक है, इसको अब मैं थोड़ा सा टेढ़ा करके अगर यूँ रखूँ तो अब जो तुम्हें फिगर दिखाई दे रहा है, मैं पीछे आ जाता हूँ, बैकग्राउंड वाइट है क्योंकि, अब जो तुम्हें फिगर दिखाई दे रहा है वो फिगर मैंने यहाँ ड्रॉ किया है. पर इसको अगर मैं एग्जैक्टली कैमरे से परपेंडिकुलर कर देता हूँ, ठीक है, तो ये एज तुम्हें नजर आ रही है. आई होप यू आर एबल टू गेट दिस गाइज. ठीक है, तो अब इसमें से जो फ्लक्स जा रहा है d5. ठीक है, इस d5 को हम कैसे लिखेंगे? यहाँ पर मैग्नेटिक फील्ड की जो डायरेक्शन है, ये मैग्नेटिक फील्ड की डायरेक्शन गाइज ये अपवर्ड है क्या? ये चेक करो, ये है क्या? क्योंकि यहाँ पर जैसे हम टेंजेंट खींचेंगे तो ऐसे अपवर्ड एरो आएगा. ठीक है, तो ये b की वैल्यू है μ0I/2πx. ये बात हमने पहले भी करी थी. ठीक है, इसको इस एरिया से, जो रेड स्ट्रिप का एरिया है, दिस एरिया इज dx into L, मल्टीप्लाई कर दिया, ये d5 आ गया. वी इंटीग्रेट d5 टू गेट द वैल्यू ऑफ phi and this integral will be carried out from R1 to R2. The value of x should change from R1 to R2. So once we carry out this integral, we are going to get some value of flux. ठीक है, इस एक्सप्रेशन में से करंट को बाहर निकाल लो. इस एक्सप्रेशन में करंट भी आएगा कहीं ना कहीं, करंट को बाहर निकाल लो. जो बच गया है वो L होगा, कोएफिशिएंट ऑफ सेल्फ इंडक्टेंस. ठीक है, सो दिस इज अनदर वे ऑफ गेटिंग द वैल्यू ऑफ L. ठीक है, तो दोनों मेथड अलग हैं लेकिन दोनों आंसर सेम देंगे. वी आर गोइंग टू गेट द सेम आंसर. एंड अगर क्वेश्चन इंडिपेंडेंटली आता, मतलब अगर सिर्फ L निकालने को कहा जाता, दिस वुड हैव बीन अ गुड मेथड. ठीक है, पर बिकॉज एनर्जी वाज ऑलरेडी आस्क्ड, ठीक है, वो हम कैलकुलेट कर चुके थे, इसलिए जो मैंने प्रीवियस मेथड बताया था, दैट वाज बेटर इन द गिवन सिचुएशन. ठीक है, ऑलराइट. सो आई होप आई एम एबल टू एक्सप्लेन दिस क्वेश्चन टू यू. आई एम एबल टू एक्सप्लेन द सेकंड मेथड टू यू. थोड़ा सा इमेजिनेशन रिक्वायर्ड होता है, इस पूरे चैप्टर में ही थोड़ी इमेजिनेशन रिक्वायर्ड होती है. सो आई होप आई वाज एबल टू गेट अक्रॉस टू यू एंड आई वाज एबल टू एक्सप्लेन टू यू. Okay, let's see the next question, guys. So this would be the answer. You can just finish the calculation and you can see for yourself. Okay, now let's have a look at this answer, this question. Okay, so again a very interesting question and a very common question too. ये जो situation है मैग्नेटिक इंडक्शन चैप्टर में बहुत ही कॉमन सिचुएशन है, इस पे बहुत सारी प्रॉब्लम्स बनती है. सो लेट्स हैव अ लुक एट दिस सिचुएशन. ओके, क्वेश्चन सेज a PQ is an infinite current carrying conductor. AB and CD are smooth conducting rods, okay, on which a conductor EF moves with a constant velocity v. क्वेश्चन में गिवन है कि constant velocity है. ठीक है, the force needed to maintain the constant speed of the EF is no gravity is there. So guys, first of all, there is no gravity, so we don't have to think in terms of horizontal and vertical, because once gravity is lost, vertical कुछ नहीं होता, horizontal कुछ नहीं होता. ठीक है, so इसको हम constant speed से लेके जा रहे हैं. तो let's try to understand the physics of the problem first. So what I can understand from here, ये जो current carrying wire है, ठीक है, इस current carrying wire की वजह से कुछ inward field इस region में inward field produce हो रहा होगा. ठीक है, अब ये तो चलो बात हो गई. अब ये EF rod move कर रही है, फील्ड इनवर्ड है, ठीक है, वेलोसिटी डाउनवर्ड है, तो F पे पॉजिटिव चार्ज कलेक्ट हो जाएगा, E पर पॉजिटिव चार्ज की डेफिशिएंसी हो जाएगी, तो ये रॉड एक बैटरी की तरह बिहेव करने लगेगी जिसका पॉजिटिव टर्मिनल F की तरफ होगा. ठीक है, सो दिस रॉड विल स्टार्ट बिहेविंग लाइक अ बैटरी विद पॉजिटिव टर्मिनल टुवर्ड्स F, सो दैट विल कॉज अ करंट फ्लो बिकॉज द सर्किट इज कंप्लीट. These parts are conducting, this is resistance, so some current flow will be there. Due to that current flow, current will also move through this rod. Please excuse me. Yeah. I'm sorry for that, guys. I'm very sure कि तुम मेरे को खांसते हुए सुनने के लिए वीडियो नहीं देख रहे हो. ठीक है, so I'm sorry for that. Okay, so current is flowing in this direction. ठीक है, अब मैग्नेटिक फील्ड अंदर है, करंट इस डायरेक्शन में फ्लो कर रहा है, तो अपवर्ड फोर्स लग जाएगा. ठीक है, आई होप यू रिमेंबर वो मैग्नेटिक फील्ड, करंट और फोर्स वाला एग्जांपल, ठीक है, जो मैंने लास्ट वीडियो में दिया था. इफ यू रिमेंबर दैट, वेल एंड गुड. अदरवाइज आई एम श्योर यू आर प्रिपेयरिंग फॉर एडवांस्ड, यू आर अबाउट टू गिव एडवांस्ड, यू ऑलरेडी नो हाउ टू फाइंड द डायरेक्शन ऑफ द फोर्स. सो मैग्नेटिक फील्ड अंदर है, करंट इधर है, फोर्स ऊपर की तरफ लगेगा. सो वी कैन सी दैट दिस रॉड इज बीइंग एक्टेड अपॉन बाय अ फोर्स ड्यू टू द प्रेजेंस ऑफ मैग्नेटिक फील्ड. ओके, एंड टू काउंटर दैट फोर्स, उसको बैलेंस करने के लिए हमें भी फोर्स लगाना पड़ेगा, और हमें उतना ही फोर्स लगाना पड़ेगा जितना ये मैग्नेटिक फोर्स है, तभी नेट फोर्स जीरो बनेगा और तभी ये रॉड कांस्टेंट वेलोसिटी से मूव करेगी. सो बेसिकली वी हैव टू फाइंड दैट फोर्स. ओके, so that is the physics of the problem. Now let's start doing the maths. Okay, so let me do it here only क्योंकि फिगर बना हुआ है. So let me do it here only. The EMF that we can see, since the rod is moving with a constant speed, the EMF that we can see here would be VLB. Now the length of the rod can be calculated using these data. B and A is given to us. So guys, what will be the length of the rod? Will it be B minus A? Okay, so VLB. Okay. Now there is a catch in this. Now there is a catch in this. As I can see, मैंने जब ये फॉर्मूला अप्लाई करने की कोशिश करा, मुझे B की जरूरत पड़ रही है. क्या इस पूरी रॉड पर B सेम है? क्या इस पूरी रॉड के डिफरेंट पॉइंट्स पर मैग्नेटिक फील्ड सेम है? सो नहीं है, डेफिनेटली नहीं है. दैट मीन्स ये अब हम डायरेक्टली तो यूज नहीं कर पाएंगे. ठीक है, इसको हम डायरेक्टली तो यूज नहीं कर पाएंगे. विल हैव टू गो फॉर इंटीग्रेशन. ठीक है, सो लेट्स डू इट गाइस. लेट्स क्रिएट सम स्पेस फर्स्ट. ठीक है, नाउ आई नीड सम मोर स्पेस. ठीक है, so let's do it here. Okay, so situation is somewhat like this. There is a wire carrying a current I. Okay, then there is a frame in which some resistance is there. Okay, and there is a rod. ठीक है, जिसकी length है B minus A. ठीक है, which is going down with a constant velocity V. So this is the situation, guys. So what I'm going to do, I'm going to take an element. यहाँ से x distance पर dx लेंथ का एक एलिमेंट लो. ठीक है, अब अगर मैं सिर्फ इस एलिमेंट के बारे में सोचूं, ठीक है, ये dx लेंथ का एलिमेंट है जिसको थोड़ा मैग्नीफाई करके बना लिया है. ये नीचे की तरफ आ रहा है v स्पीड से, और इसमें जो EMF इंड्यूस होगा, ठीक है, इसमें जो EMF इंड्यूस होगा, दिस EMF विल बी रिटन एज VL. L will be dx. Okay, and B will be mu naught I by 2 pi x. What do you think, guys? ठीक है, इस जगह पे मैग्नेटिक फील्ड इस वायर की वजह से म्यू नॉट आई बाय 2 पाई एक्स, राइट. सो डी इज गिवन बाय दिस वन. ओके, इफ वी इंटीग्रेट इट नाउ, इफ वी इंटीग्रेट like to get the total EMF that has been generated in the rod, ठीक है, we can write E as DE1 plus DE2 plus DE3 and so on. ठीक है, मतलब you can see that these small segments, they will act as small batteries that are connected in series. Okay, so this will be given by integration of mu naught I by 2 pi x and v dx. ठीक है, तो यहां से अगर मैं इंटीग्रल पूरा कर दूं, म्यू नॉट आई बाय 2 पाई बाहर आ जाएगा, v बाहर आ जाएगा. ठीक है, और जो लिमिट्स आएंगी वो a टू b आएगी. सो ये हो जाएगा ln b बाय a. ओके, सो दिस इज द मैग्नेटिक, दिस इज द EMF दैट वी आर गोइंग टू गेट. ओके, नाउ व्हाट एल्स इज रिमेनिंग. ठीक है, अब जो करंट फ्लो करेगा, जो करंट इसमें फ्लो करेगा, ठीक है, इस डायरेक्शन में जो करंट फ्लो कर रहा है, ठीक है, इस डायरेक्शन में जो करंट फ्लो कर रहा है, ये करंट होगा EMF बाय R, ठीक है, ये हो जाएगा EMF बाय R, ये करंट आ गया। अब जो फोर्स लगेगा, ठीक है, अपवर्ड डायरेक्शन में लगेगा फोर्स, अपवर्ड डायरेक्शन में लगेगा फोर्स, दिस फोर्स इज गिवन बाय ओके, ये फोर्स भी हमें इंटीग्रेशन से निकालना होगा गाइस, ठीक है, क्योंकि अगेन हमें BIL करना है, लेकिन B तो डिफरेंट है, तो फिर से कंसिडर दिस एलिमेंट ओनली। इस एलिमेंट पे ही फोर्स लिखते हैं पहले, इस एलिमेंट पे ऊपर की तरफ जो फोर्स होगा ये हम लिखेंगे, फिर से देखो म्यू नॉट आई, ओके, let me avoid using blue pen because there was a feedback that blue color was not visible, so okay, so df will be mu naught I by 2 pi x, तो ये b हो गया, into I prime is E by R into dx, ठीक है, सारे एलिमेंट्स पर एक ही डायरेक्शन में फोर्स है, so we are going to integrate this expression and we are going to integrate this expression within the limits from A to B. Once we are done with this integration, we are going to get the result. Okay, and I'm again leaving it here. I'm very sure that you can finish the calculation. I hope I have explained you the physics of the problem, and I've also done the majority of part of the calculation, the typical calculation, like wherever integration was required, I've told you that. I just expect you to finish this integration to get the result. All right. Okay. So on completing everything, this is what you are going to get. All right, guys. Okay. So let's have a look at this question now. Okay. So a resistor and an inductor in series are connected to a battery through a switch. Okay. After the switch is closed at T equal to 0. So guys, this seems to be a very straightforward question. LR circuit का question है. There is a battery, there is an inductor, there is a resistance. We are all aware of it though, but देखते हैं options देखते हैं, ठीक है। Options actually थोड़े से interesting है, especially option A guys, pay very very particular attention to option A because this is a very good option. It says joule heat dissipation in the resistor changes at fastest rate. Okay, changes at fastest rate. Joule heat dissipation in the resistor changes at fastest rate. So guys, let's try to see what this A option has to say. Okay, we are aware that in this case, in this LR circuit, the equation that we write for current would be V by R, then 1 minus e raised to power minus RT by L. पहले तो ये देख लो, are you aware of this equation guys? I hope you are aware. ठीक है, T को अगर हम 0 डाल देते हैं, current will be 0, which is actually the case. Just after closing the switch, the current remains 0, but after infinite duration, the current will become V by R. So this equation tells us everything. Okay, so this equation is already available with us. Now if I have to write the power developed in resistor R, the power developed in resistor R will be given by I square R. So we can substitute this in place of I. We can do that. Now what does this question says? This question says that joule heat dissipation changes at fastest rate. So guys, first we have to find the rate at which this power is changing. Okay, so you are going to get a function of time here. Okay, once you do the math, you are going to get function of time here. Okay, I'll be doing the math on the next slide because space is not available on this one. I'm telling you the procedure here. So this will give us the rate. Now we want the fastest rate. So we want the maximum value of this function ft. Are you able to understand this one guys? हमको एक बार डिफरेंशिएट करेंगे तो हमको पावर चेंज होने की रेट मिलेगी। जब हम दोबारा डिफरेंशिएट करेंगे तब उस रेट के मैक्सिमा या मिनिमा की वैल्यू हमें मिलेगी। ठीक है, सो वी हैव टू डिफरेंशिएट दिस एक्सप्रेशन ट्वाइस and we have to equate it to 0 from by this equation. By solving this equation, whatever value for t we are getting, we will substitute that value of t in this very expression. Actually that t is only required, that t is required right there. Okay, so this is how we are going to solve for option A. ठीक है, we'll do that. Option B पढ़ लेते हैं. Option B says when the rate of increase of magnetic energy stored in the coil is at maximum, okay, the current in the circuit is okay. Now again B option भी similar बात कर रहा है. ठीक है, मैग्नेटिक एनर्जी जिस रेट से स्टोर हो रही है उसके मैक्सिमम, तो सिमिलर चीज है। ठीक है, वी आर गोइंग टू राइट मैग्नेटिक एनर्जी एज हाफ Li स्क्वायर, देन वी आर गोइंग टू डिफरेंशिएट दिस एक्सप्रेशन, दिस विल गिव अस द रेट एट विच मैग्नेटिक एनर्जी इज बीइंग स्टोर्ड। सो ये तो रेट आ गई, अब रेट को भी मैक्सिमाइज करना है, वी हैव टू फाइंड द मैक्सिमम वैल्यू ऑफ दिस रेट, सो वी विल डिफरेंशिएट इट अगेन। सो व्हाटएवर वी आर गोइंग टू डू विद PR, whatever we are going to do with the expression for thermal power, we are going to do the same thing with the expression for energy stored in inductor. We will differentiate it once, we will get the rate of increase of magnetic energy. Then we have to find the maximum value of this range of this rate. So we will differentiate it again and we will equate it to 0. So we will do that on, okay, let's just go through the procedure once. C option says power dissipated in the resistor increases continuously. Power dissipated in the resistor increases continuously, but rate of change of power initially increases, it later reaches a maximum and beyond a point decreases to 0. So guys, जो C option है, that is actually related to A option, because while writing A option, while finding out the answer to the A option, we'll be doing these calculations. Okay, we'll be differentiating this power once, we'll be differentiating it again. Okay, so this part seems to be true, that power dissipated in the resistor increases continuously. Okay, power dissipated. So C option says that PR goes on increasing. If PR goes on increasing, that basically means current goes on increasing, and that is basically true also. If we draw a graph of this one, I hope you remember that the graph will be an exponential graph, exponentially increasing graph, which attains the value of V by R increasing from 0. So current in this circuit is definitely increasing continuously, eventually getting saturated at a value of V by R. Okay, so that means power will also increase continuously, that is fine. But the rate of power initially increases, reaches a maxima and beyond a point decreases to 0. So guys, as of now C option मुझे लग रहा है सही निकलेगा, because C option A से related है. जैसे A उस टाइम की बात कर रहा है जब पावर के चेंज होने की रेट मैक्सिमम थी, ठीक है, तो यहाँ पे भी उस रेट की ही बात की गई है कि रेट मैक्सिमम वैल्यू अटेन करेगी फिर 0 पे आ जाएगी. So while doing A, we will also take a call on C. We will also decide whether C is correct or not. Okay, that will be done while doing A option itself. Now let's have a look at D. Okay, the fastest increase of current takes place. तो fastest increase of current, तो di by dt की maximum value चेक कर रही है हमें. I don't think ये बहुत difficult काम होगा. di by dt निकालकर हमको just देखना है कि di by dt की maxima कब आएगा. ठीक है, so these are the 4 options that are present in this question. So each of this option is a special one, like it requires some calculation. सिर्फ A और C जो है वो related है, मतलब कि A और C एक ही बार में पता लग जाएंगे. इसके लिए एक independent calculation करनी पड़ेगी, D के लिए एक independent calculation करनी पड़ेगी. Let's start doing that, guys. ठीक है, let's start doing that. Okay, so let me do it here. So the expression, okay guys, ये हम next slide पे चले गए थे. Okay, so the expression for current that we are going to get would be V by R, then 1 minus e raised to power minus RT by L. Okay, so I'm going to try the D option first because it seems an easy option. So let me do with di by dt. So di by dt would be V by R, then 0, and then it is going to become, one negative will appear, so it is going to become plus, and then R by L, then e raised to power minus RT by L. Okay, so it ultimately becomes V by L, okay, into e raised to power minus RT by L. So you can check this, guys. So this is the equation. I hope I have done everything correct. Just let me double check it. Differentiation part is correct. Okay, so this is the rate of change of current, and I can see that this graph is an exponential graph. At t equal to 0, the value is V by L, and since after that it goes on decreasing, becoming 0. Okay, so this rate will be maximum. This rate will be maximum at initial instant only, and that maximum value will be what? That maximum value will be V by L. Okay, so that maximum value will be V by L. Okay, we'll just check whether D option said so or not. Okay, so this is, we have checked the D option. I think, okay, this is, we have checked the D option. Now let's check the A option. Okay, so for A option, we have to find the expression for PR, that would be I square R, and we have to find dpr by dt. So this is what we are supposed to do. I'm doing it indirectly. Okay, you can substitute I in place of like you can substitute this entire expression here, then you can differentiate. That you can always do, but we can also do this. What do you think? 2 times of I into di by dt. What do you think, guys? Can we do this one? Chain rule. Okay, so this is going to become 2r. The expression for I is V by R 1 minus e raised to power minus RT by L into di by dt. Di by dt is this one. So V by L and then e raised to power minus RT by L. Okay, So this is what you're going to get. R will get cancelled. Okay, and we are ending up with what? Just a minute, guys. Okay, so we are ending up with what do you think, guys? We are ending up with 2v square by L and then 2v square by L and e raised to power minus RT by L minus e raised to power minus 2 RT by L. What do you think? This will go inside. Okay, so this is the expression for dpr by dt. Now what we have to do to find out whether A option is correct or not, we have to differentiate this one again and we have to equate it to 0. So let me do it here. D square PR. I think I'm going to fall short of space. So these are some constant value. We can just write it. To save space, I've done this. We need not write this entire thing. Okay, the derivative of this one will be what? Derivative of this one will be minus R by L e raised to power minus RT by L and then plus 2R by L e raised to power minus 2RT by L. Okay, we equate it to 0, we get the expression. Okay, on equating it to 0, what are we going to get? Let me do it here. Okay, so let me create some space here. Okay, so I'm changing the ink color so that you are able to differentiate what is the newly written thing and what was written beforehand. So when we equate it to 0, what are we going to get? We are going to get e raised to power minus RT by L, that is equal to, okay, I'm doing some calculations mentally only. I think that is equal to half. What do you think, guys? One of the e raised to power minus RT by L will be taken out. Okay, and then yes, this is what we are going to get. So taking log on both sides, we are going to get T as L by R ln 2. So this is what we are going to get. Okay, so if option A says this value, then option A is correct. Now we can also see that since we are getting a value of maxima, okay, this is definitely the value of maxima. You can confirm it. How you can confirm it? Like initially the current was 0, so initially power was also 0. Power cannot be negative. So from a 0 value it attained a positive value and then eventually it again became 0. So definitely a maximum will be there. Minima can't be there. So this is the time when power, rate of change of power attains a maximum value. Okay, and so definitely this power increased and then it decreased. So C option is correct, A option is correct, D option we have already checked, B option is left. So let me do it here. I think we needed this one. I think I've just messed it up because I've erased something that I was going to need. Okay, so U will be written as half Li square. So du by dt will be what? Du by dt will be L into I into di by dt. Guys, I'm leaving it for you guys now because I'm very sure that you are also bored of this question now because we are doing primarily maths. But this question is important because it tells you that sometimes in questions you may be required to differentiate twice depending upon what has been given or what has been asked in the language. Okay, so you need to interpret the language appropriately and then you should start doing the math. So di by dt we already calculated, we substituted here, we get the rate, then we differentiate it again, we equate it to 0. We'll check the options, you'll get the answer. Okay, straightforward question. Once you understand or once you realize what you are going to do, then the question is pretty straightforward. So guys, let me just check the option. So we were getting this one only for time, so this one is correct. I think D option is incorrect because for D option we were getting something related to V and L. I think it was V by L as far as I can remember. So A is correct, C is correct, D is definitely incorrect. B, I think you'll get it correct once you do the calculation. I did not finish the calculation. I've told you the method, you can complete it on your own. I believe you can do it on your own. Okay, so let's just confirm the answer. So yes, so you're going to get A, B, C as the correct answers. Alright guys, okay, so I believe that is done. Now comes a question. This is one of my favorite questions. I just absolutely love this question and you'll find out why, because it actually requires a knowledge of a lot of concepts, and even if you have the knowledge of the concepts, the application part still remains, that is to be done correctly in this particular question. Okay, so let's just see what this question says. So the question says a solenoid of radius 2r containing another coaxial solenoid. Okay, so there are two solenoids, one of radius 2r, the other of radius r. Their coils have the same number of turns per unit length and initially both carry no current. At the same instant, current starts increasing linearly with time in both the solenoids. At any moment, the current flowing in the inner coil is twice as large as the outer one and directions are same. As a result of the increasing current, a charged particle initially at rest between the solenoids starts moving along a circular trajectory as shown. Okay, the current in the outer coil is given by kT. Mass of the particle is m, charge is q, then the induced electric field. Alright guys, so we have read the question. The figure is here. So situation is like this. This is a solenoid, okay, and we are looking from one end of the solenoid. Okay, so this is a solenoid carrying a current 2I. This is another solenoid, and this is carrying a current of I. Okay, so if these solenoids are carrying current like this, let's first try to understand in which region these solenoids are going to produce magnetic field. So this inner solenoid, assuming that it's an ideal solenoid, this inner solenoid is going to produce a magnetic field within itself only, and the direction of that magnetic field would be inwards. So we can expect crosses in this region. Okay, we can expect crosses in this region, and this is because of the inner solenoid. Okay, now the effect of outer solenoid. I'm drawing the magnetic field lines due to the outer solenoid. Okay, like the outer solenoid will create a magnetic field in this region and in the inner region also. Okay, I hope you understand this one, guys. Okay, so the outer solenoid will create magnetic field in the entire region. The inner solenoid will create magnetic field only in the region which is inner to itself. Okay, so this is one thing. Now the next thing is current in both is increasing linearly. So when the current starts increasing in both, magnetic field will also start increasing both. Okay, now comes the catch. Okay, one may be tempted to believe that in this region only the magnetic field due to the outer solenoid is there. Hence, when we are calculating the electric field present in this region, we should consider the magnetic field due to the outer solenoid only. You may be tempted to believe this, but hang on guys. This is like, you should be cautious here. The electric field that will be produced in this region will be because of both. Okay, if you have studied this in theory, I hope you have done this. If there is a region in which magnetic field is there, and let's say if it's increasing with time, okay, then the electric field that we get, okay, if it's increasing with time, then the electric field we get in this region also, okay, and in the outer region also, if you can remember that guys. ठीक है, मतलब मैग्नेटिक फील्ड चेंज होने से जो इलेक्ट्रिक फील्ड इंड्यूस होता है नॉन कंजर्वेटिव होता है, और वो दोनों रीजन्स में आता है. अगर ये रीजन आर रेडियस का है तो इस इलेक्ट्रिक फील्ड का एक्सप्रेशन हम लिखते हैं स्मॉल आर बाय टू. वी राइट स्मॉल आर बाय टू dB by dt when small r is less than r, and we write r square by 2r. ठीक है, दिस इज स्क्वायर, थोड़ा मिसप्रिंट हो गया, into dB by dt when r is more than Kepler. So this is the formula that will be used in solving this particular question. If you are not aware of this formula guys, you should be aware of this one. Like you should scramble for some books or notes of somebody who has this thing covered, and you should go through this entire theory. Okay, so this is the expression that we will be using in solving the question. I am rubbing the expression for now. Okay, I hope you have noted it down. If you have not noted it down and you were not aware of it, you can just watch the replay again. You can pause the video and you can note it down, and then you can get in touch with someone who is learned enough to teach you this concept. Okay, so we were discussing, so let's say this distance is small r. So at this particular point, the electric field that we are going to witness, see, because of the inner solenoid, what I would be writing, because of the inner solenoid, I would be writing capital R square by 2 small r into dB by dt. So mu naught and n will come out, and it is going to become 2 times of di by dt. I hope you understand this one. The magnetic field, the B due to this one will be written as mu naught and I will be 2i actually. So this will become the derivative. So this is the contribution of the inner solenoid. The contribution of the outer solenoid will be r by 2, since this region is inner to the outer solenoid. So r by 2 into dB by dt. So mu naught n and then di by dt. So this is what we are going to write for electric field. Okay, all right. So this is what is written here. I think there is some misprinting in this question. Why I'm saying so? Because these options do not contain this kind of expression. Okay, So what I believe probably, okay, yeah. Question says R is less than capital R. So when R is less than capital R, right now in this particular question, we are not discussing the electric field that will be that will act on the particle. We are discussing electric field in the inner region. So in the inner region, here also we should use the same expression. Okay, so let me just rub this expression if I can. Yes, I can. And R by 2, it will be R by 2 because this we are discussing magnetic field in the inner region only. So guys, what do you think? What are we going to get? This will solve to become, this is what, K, di by dt. Di by dt is K. So this is also K. So I think we are looking at 3 by 2 mu naught N R K. Do we have such an option? 3 by 2 mu naught N K R. So I think A option would be correct. So in this, for this particular question, A option should be correct. Okay. I hope you got this one. I hope I got this one. And yes, I did got this one. Okay. All right. So this one is correct. Now let's see the next part of this problem. Okay. The next part says radius of the charged particle. Now this is a tricky one. This is a tricky one. Okay. We'll have to understand what is going on. Will have to understand what is going on. So let me first tell you the physics of the problem. Okay. We have written down the value of E here. In the previous question, while solving the previous question, I inadvertently wrote down the electric field at this point. Okay, we'll be using that expression. Let's try to understand what is going on. So a charged particle was here. The magnetic field started changing. That resulted in an electric field. In which direction? So inward field is increasing. We can expect the electric field to be tangential. Like these are the directions in which we can expect force to act. Like you can expect tangential forces on the particle at every point. Okay. So these forces are going to increase the speed of the particle. Okay, so we can say that Q times of E, that is the force. Okay, and this force divided mass is acceleration. Okay, and since the force is always tangent, so the force is always tangential, so we multiply it with T and we get the value of speed of the particle. Okay, so you understand this one? We get the speed of the particle. Okay, now apart from the electric force, there will be a magnetic force also because of the magnetic field present here. Magnetic field is there, direction of velocity is this, force will be inward, and this force should be equal to what? This force should be equal to mv square by r because the particle is executing circular motion. So what I'm going to write, I'm first going to write the expression of this magnetic force by using the expression of qvb. Okay, so I'll be writing q, okay, then v. Let me write in terms of v first. QVB, the B here would be because of the outer solenoid only, so that will be mu naught N into I. Okay, so QVB is the force equal to mv square by small r actually. Okay, this small r. So this should be the expression. So we cancel out this one. Okay, so now we are looking at. Okay, I'm again using the blue pen. Forgive me for that. Okay, Q mu naught N. In place of I, we are going to write KT. Okay, and then M by R and V. V will be written as QET by M. Okay, so M gets cancelled. This T gets cancelled. So we can see here, from here we can get the value of R. Okay, we can get the value of R in terms of E. Okay, so this thing we can do, we can get the value of R in terms of T. Let me see if I can rub this question. No, I'm sorry. Okay. Now E we have already written on the previous page while solving the previous question. Okay, so that expression we can substitute here, but since this is a difficult question, I want to do that for you guys. So let me just use this equation here. I'm rubbing the upper part and I'll be doing it here. Here's my duster. Okay, so from here we are going to get an expression for R, and this expression would be like, okay, Q will also be cancelled. Okay, so this expression will be E divided by mu naught N K. Okay, so this is the expression that we are getting. Now I'll write the expression of E, the expression that I have written in the previous question. Okay, the expression at outer region, because of this inner solenoid, we are going to get R square by 2R into mu naught N, and it is 2I. So this is 2 times of K it is going to become. Di by dt. Di by dt is what? K. Okay. So this plus the electric field due to the outer solenoid, and that will be what? That will be small r by 2 into mu naught into n into K. So this entire thing divided by mu naught n K. So guys, what do you think? What all is getting cancelled? What all is getting cancelled, guys? So mu naught n K, mu naught n K, mu naught n K is getting cancelled, and we are left with r square by 2r plus r by 2, and this entire thing equal to r. I believe you can solve this equation. On solving this equation, you are going to get the result, and I don't think solving it is a very difficult task. Okay, I can do it here only. If I multiply this equation by r, we are going to get r square minus r square by 2. So that's r square by 2 is equals to what? Something wrong or what? I think I messed it up. Somewhere I messed it up. Solving this, what we are getting? R square minus r square by 2. So that's r square by 2. I think I've messed up the calculation somewhere, and that is not. Let me check this expression only. R square by 2r mu naught n into idb by dt. So that will be okay. Yes, it's here only. Like not somewhere earlier. This 2 gets cancelled. Okay, so we end up with. Yes, sorry for keeping you wait. Okay, so this is going to end up with this. So we are looking at root 2r. A option is correct one. Okay, so I hope you got this question. This was a very good question, a brilliant question, as it contained multiple aspects, multiple concepts. Okay, it used that concept of force on a charged particle, magnetic force on a charged particle, causing it to move in a circle. It used the concept of electric field, the expression for electric field, and the fact that we have to write the electric field due to both the solenoids. So it's a very good question. It is a question that can stump you at multiple stages. Like even if you are able to avoid 1 or 2 pit holes, then also there's a good chance that you get stumbled upon one of those. Okay, so a very good question to be given an exam if the examiner wants the student to falter. Okay, all right. So yes, A is indeed correct. Okay, now there's a third part also. The speed of the particle as a function of time. I think guys you can do it now, because we've already figured out that speed would be speed will be QE by m into t. We can find E now because we are aware of small r. Okay, we have calculated small r as root 2r. We can substitute that value of small r in the expression for E, and we can just substitute the whole thing here. From there you can just finish the calculation, you'll get the result. Okay, so I think you can do this part on your own. So I'm skipping this part. Actually, we have already solved this part while solving the previous parts. Okay, just some little substitution needs to be done, so you can do that. So you are going to get B as the option. All right, now finally I think this is the last question that I've brought. So let's have a look at this. This is one is based on AC. Okay, so I think it's a straightforward question. Let's just have a look at it. Figure shows a series LCR circuit connected to a variable frequency source. Okay, 200 volt source. So guys, one of the things that I would like to ask you, what is this 200 volt? Like, is this the RMS value or is this the peak value? So I hope you are aware that if nothing is mentioned, we consider the given value to be the RMS value. Okay, so this variable frequency 200 volt source, L is given, C is given, R is given, and the impedance of the circuit at resonance. So guys, what happens at resonance? At resonance, these two cancel out each other's effect, and the impedance becomes equal to the value of the resistance. So resistance is 40 ohm. So A option is definitely correct. Okay, the current amplitude at resonance is this. So at resonance, again, the entire impedance gets converted into the resistance only. Okay, so if 200 volt is the RMS value, okay, then at resonance, the RMS current would be 200 divided by 40, so 5 ampere. So this will become the RMS value. The option B says this is the current amplitude. So option B says that this is the peak value. So this is definitely wrong, because we are getting 5 ampere, but this is the RMS value, not the peak value. Okay, so B is incorrect. A was correct, B is incorrect. The RMS potential drop across the inductor at resonance. Okay, so at resonance, the RMS value of current is this. Okay, so to get the RMS value of potential drop at inductor, we have to multiply this current with inductance. Okay, with XL we have to do. And what is XL, guys? XL is omega into L. And at resonance, what will be the value of omega? Is it 1 by root LC? Okay, so this is what we are supposed to do. So 5 root L by C. We finish this calculation and we'll be able to decide on option C whether it's correct or not. So let me do this. So L is given to be 5 Henry, C is given to be 80 microfarad. So it becomes 10 to the power 6 after going into the numerator. Okay, so we are now looking at 5,000. This 10 to the power 6 becomes 1000 divided by 16. So it becomes 4. So I think this option is correct because 5000 by 4 will end up in 1250. So C option is correct. D option says RMS potential drop across the resistor at resonance. Okay, so RMS current is this one. You multiply this current with the value of R, that is 40. So you are going to get 200 volts. So yes, D option is correct. Okay, so we have seen C option is correct, D option is correct, A option is correct, B is incorrect. All right, so that is what our answers would be. And yes, they are indeed the answers. All right, so I hope guys you enjoyed these questions. I hope I was able to tell you something that you did not know before. And if you knew everything, that's absolutely fabulous, because that it means that you are well prepared. I was not able to figure out anything, or I was not able to bring anything that was new to you. You are well prepared. You are absolutely well prepared. So keep it up. Just keep doing what you are doing. Only a small amount of time is left before the JEE exams hit us, advanced exams hit us. Okay, so I wish you all the very best for your examination. I hope you pass this exam with flying colors, you secure a very good rank, and you get the stream and the college of your choice. That is my wish for you guys, for each of you guys. And on that note, I'll bid you farewell. I'll bid you goodbye. This is the end of the Electrodynamics series, and the Aspire series will be continued by my friends, by my colleagues. And I bid farewell to you guys now. All right, guys. Again, download our app, make use of it, like, share, and subscribe. On that note, I bid you bye-bye. Thank you. Have a very good evening.